as we hinted last time, we are curious about the local maximum. Remember that it's local. It's a maximum right here, but of course there are things that are higher, so it's a local max. It's not the absolute maximum, but it's a local maximum. And here's the local minimum. It's not the absolute minimum because there are things lower, but it's a local minimum. And we're curious about where these things happen. And I think this is somewhat interesting. If we have degree, let's say we have degree 5, then there's going to be, at the most, 4 turning points. One less. There's always one less turning point. If we look up here and we say there's 2 turning points, this might be x to the 3rd. Probably is. Or it could be, it could be other things. But at the most, x to the 3rd would have 2 turning points. It doesn't get 3. All right. So anyway, if a polynomial function has n distinct real zeros, no kisses, no. If it has n distinct real zeros, then its graph has exactly n minus 1 turning points. All right. Estimate the coordinates of each turning point and state whether each corresponds to a local maximum or a local minimum. Then estimate all real zeros and determine the least degree the function can have. The least degree. All right, so that's 3 things. First thing is estimate the coordinates of each turning point. Okay, well, here's one down here. So I suppose that would be, looks like each block is worth 1. So that doesn't look like it's right in the middle, does it? Not to me, it doesn't. It looks like I'd have to call this for the turning point, and this is a minimum, right? We have a minimum at negative 1 2/5, I guess, if I wanted to get all fancy. And it's down, it looks like, well, it looks pretty close to 1 2 3 4 5 down here, negative 5. But it might be a little bit more. 5 1/4. No, it wouldn't be 5 1/4. Maybe 5 1/5. We're just guessing here. It might be exactly negative 5. And there's also a maximum here. That is not on the line, so it's not negative 2. And it looks like that's maybe for our maximum at the hilltop there, we'd say, oh, what do you think? Negative 1/4, maybe. And it looks like it's down at about, oh, who knows? It's pretty close to negative 2, but it's not. It's negative 1, we'll say 7/8. We're just guessing here, we're coming close. And down here is a minimum, another minimum. And let's see, that looks like a positive half. We'll just be nice. And positive half, and looks like this is negative 3, right? So let's say that's negative 2.5. Any other turning points? No, there are no other turning points. Estimate all real zeros. Well, that sure looks like a negative 2 to me. So I would say I'd get a negative 2 0. There's one of my zeros. And that looks like 1 to me. I'd also say that I have a 0 at 1. And of course the y is a 0. That's why we call it a 0. It's hitting the x-axis somewhere where y is 0, because it's on the x-axis. Now let's see. Determine the least degree the function can have. Well, it's got 2 zeros. So that right there would tell me it's at least x squared, right? But wait, there's more. There's 3 turning points, right? 3 turning points. So it's possible that this thing, the fact that there are 3 turning points, that would lead me to believe that it could be x to the 4th. So x to this, that's too little, the idea of 2 zeros. And then just for fun, I would also say If I put my x-axis there, I'd have 1, 2, 3, 4 places anyway. You know, if that were my x-axis. So I'm going to go ahead and say the least degree that this thing can have, I'm going to say 4th degree. 4th degree. Yeah, 4th. Don't know how to spell 4th. 4th degree. And I think, is that all they wanted? Yes. We identified whether they were local maximums, minimums, the least degree the function can have. We estimated the zeros. Well, that was the only clear thing on this graph, I think. And that's it.